Hello viewers, in this presentation we are going to discuss second law of thermodynamics and heat engines. The second law of thermodynamics is a statement about which processes occur in nature and which do not. It can be stated in many ways and these statements are equivalent. Heat flows from a hot body to a cold body. Heat will never of itself flow from a cold body to a hot body. The following diagram shows heat flow from a hot reservoir to a cold reservoir is allowed, but the reverse is not allowed. Another statement of the second law of thermodynamics states that when work is done by a heat engine running between two temperatures, only some of the input energy can be converted into work. The rest is rejected as heat to a cold reservoir. The schematic of this statement is shown above. Whenever a physical system is allowed to distribute its energy freely, it always does so in a manner that disorder increases, that is, entropy increases. Suppose we have a box partitioned into two with a gas in one of its side and the other side evacuated. As soon as the partition is removed, the gas molecules will distribute themselves throughout the box and be moving in a less ordered situation. We say that entropy of the gas has increased because the amount of disorder has increased. Entropy is a measure of the disorder of the system. All the natural processes are irreversible, and in all cases entropy increases and some energy becomes unavailable to do useful work. Mathematically, change in entropy can be measured as delta S equal to Q by T. The building block of a heat engine is shown here. The heat engine absorbs heat from a reservoir of higher temperature, converts some amount of its heat into useful mechanical work, and discard the remaining energy to some low temperature reservoir called sink. Heat engine continuously converts heat into mechanical work by taking some working substance around a cycle. Thus, the net work done by a gas in any closed cycle is equal to the area enclosed by the closed loop in PV diagram. Therefore, net work done by an engine is W equal to QH minus QL. The efficiency of any heat engine can be defined as the ratio of the work it does to the heat input at the higher temperature, that is eta equal to W by QH, which leads us 1 minus QL by QH. Carnot's cycle is of great importance from both theoretical and practical standpoint. We know work could be done only when heat flowed from a higher temperature to a lower one. CARNOT in 1824 proposed an ideal engine that operates cyclically and reversibly between two temperatures. A Carnot cycle consists of two reversible adiabatic and two reversible isothermal processes operating between temperatures TH and TL. We know efficiency of a heat engine in general can be written as eta equal to 1 minus QL by QH. Now, heat energy QH supplied to the gas during the isothermal expansion AB is QH equal to WAB equal to nRTH ln VB by VA. During isothermal compression, the amount of heat QL is expelled, which is equal to QL equal to nRTL ln Vc by Vd. For adiabatic changes, T v to the power gamma minus 1 is equal to constant. Applying this fact to the adiabatic processes Bc and Da, we can write down Vb by Va is equal to Vc by Vd. This leads us to the expression for the efficiency of a Carnot engine, which is eta equal to 1 minus TL by TH. The expression suggests that 100% efficiency can only be achieved if TL is equal to 0 Kelvin. This is of course impossible. Therefore, efficiency is always less than 100%. A device that converts 100% of input heat into mechanical work is physically impossible. This statement is also considered as another statement of second law of thermodynamics. All reversible engines have same efficiency when operated between the same set of temperatures, regardless of their working substance. The efficiency can be increased by decreasing the factor TL by TH, that is, taking heat from a heat reservoir at very high temperature and rejecting to a very cold reservoir. The Carnot cycle is the most efficient cycle of all reversible cycles operating between two fixed temperatures. No engine working between two temperatures can be more efficient than a Carnot's reversible engine working between the same temperatures. Consider the cycle shown in the following figure. From point A, the gas expands along the line AB, neither an adiabatic nor an isothermal path. As temperature decreases from TH to TL, this is followed by an isothermal compression to point C, and then adiabatic compression, which returns the system to starting point A. How does this reversible cycle compare in efficiency with the Carnot cycle between the same temperatures? The adjacent figure shows how expansion AB can be approximated as closely as we wish by a series of small isothermal and adiabatic steps. We then replace the reversible cycle by small adjacent Carnot cycle shown in the second figure. The efficiency of any one of these small Carnot cycle depends upon its upper and lower temperatures. The upper and lower temperatures of any small Carnot cycle is less than that of the actual Carnot cycle. Therefore, for any non-Carnot reversible engine, eta is always less than 1 minus TL by TH. Heat engines can be divided into two classes. These are external combustion engine and then internal combustion engine. In external combustion engine, the working substance, that is steam, is produced by burning the fuel outside the cylinder. The steam engine is an external combustion engine. In an internal combustion engine, fuel is burned inside the cylinder. Petrol engine and diesel engine are examples of internal combustion engine. Efficiency of a petrol engine can be represented as eta equal to 1 minus 1 divided by V2 by V1 to the power gamma minus 1. Here V2 by V1 is equal to adiabatic compression ratio and gamma is Cp by Cv for the gas. A refrigerator is a heat engine running in reverse, that is, it transfers heat from a colder body to a hotter body. The principle of refrigerator is shown here. The effectiveness of a refrigerator is measured by its coefficient of performance. The coefficient of performance is defined as the ratio of heat extracted per cycle at low temperature to the work input required. That is, COP is equal to TL by TH minus TL, or in other words, COP equal to 1 minus eta by eta. To summarize, in this presentation, we have discussed second law of thermodynamics, concepts of entropy, Carnot cycle, engines and refrigerator.